The question says a magnetic moment of 1.73 Bohr magneton will be shown by one among the following. Which complex has magnetic moment value 1.73? And always keep in mind, magnetic moment value depends on the number of unpaired electrons. As the n value increases, number of unpaired electrons increases, magnetic moment value also increases. Keep in mind, if the complex has only one unpaired electrons, okay, if our complex has only one unpaired electrons, magnetic moment value will be 1.73, and if two unpaired electrons are there, magnetic moment value will be 2.8, and three unpaired electrons, magnetic moment value 3.8, four unpaired electrons, magnetic moment value will be 4.8. okay, so now you can see, if the complex has one unpaired electrons, then we can get 1.73. And remember this value, it will be quite easier, it can save the time. And you can see in the same pattern we are getting the value. It is also, if you can see, it is also 1 point in the pattern of 0.8 it is coming. 1.7 is there, almost nearby. Okay, 2.8, 3.8, 4.8, and next if you are going, it is 5.9 is there. So it's very easy to remember. Okay. Now we can find out the number of unpaired electrons, and to find out the number of unpaired electrons, we apply the valence bond theory. Okay, to apply the valence bond theory, we follow the step. What are the steps? First, we calculate the oxidation number of the central metal atom. Next, we write electronic configuration of the central metal ion, and next we have writing orbital notation. And before notation is there, before filling electrons in orbital notation, we consider the effect of ligand, whether we have a strong field ligand or weak field ligand. Strong field ligand means pairing of electron, and weak field ligand means no pairing of electron. Okay, we come to the first complex, and always keep in mind, we have ammonia neutral ligand. Of course, ammonia acts as a strong field ligand, but it does not act as a strong field ligand with all the metals. It acts as a strong field ligand only with selective metals, and those metals are, we have cobalt, cadmium, and copper, and Fe is there. Only with these metals it is acting as a strong field ligand. Keep in mind. Okay, then we have copper is there. Here we have copper, means we have to consider it as a strong field ligand. Okay, follow these steps. Calculating oxidation number of the central metal atom. Let's calculate. We have copper is there, plus this is neutral ligands, 4 multiplied by 0, overall charge is what, +2. Then copper is present in +2 oxidation numbers. Okay, next we write electronic configuration. Copper atomic number is what, 29. Then we have electronic configuration 3d10, and its 4s1 is there. Copper is having +2 charge, then losing 2 electron, it will be 3d9 is there. 3d9. Now we can go for the orbital notation. Cu2 plus is there. Writing orbital notation, we have 3d9 is there. 3d9 is there. 3d9. Before filling electrons, we need to consider the effect of ligand. We can mention 4s. Anyway, it is not required. And 4p, these are the vacant orbitals. 4p. Okay. Because we are not going to determine hybridization, we are going to find out the number of unpaired electrons. Okay, so 3d9 is there, and we start filling electrons. How we have to fill the electrons? Look at the effect of ligand. You can see we have a strong field ligand, means pairing of electron will be taking place. So electrons we have to fill by pairing of electron, ignoring Hund's rule. 2, and it is 4, and it is 6, and it is 8, and it is 9 is there. It has only one unpaired electrons. We can see we got the answer in the first option itself. Okay, if the complex has only one unpaired electrons, magnetic moment value will be 1.73. And how we determine magnetic moment? That formula, mu is equal to, we have under root and n bracket n plus 2, and this is what Bohr magneton is there. In this formula, if you plug in n is equal to 1 and simplify, you will get the final value 1.73. Similarly, if n value is 2, if you plug in here n is equal to 2, then if you simplify, you will get 2.8. And it's very easy to remember. You can see in the 0.8 pattern, these values are given there. 1, 1.7, 2, 2.8, 3, 3.8, 4, 4.8, 5, 5.9. It is also nearby 0.8. Okay, so like that. And beyond 5 you will not get any question, because d orbital maximum can have only 5 unpaired electrons. So beyond 5 unpaired electrons, you will not get any complex. Okay, so very easy to answer. For the rest also, if you want to do it, you can do it, but in all these cases you will not get one unpaired electrons, because this is what, only one option will be correct. So we got the first option. This is the method we follow. We follow these steps to find out the number of unpaired electrons. We use this formula, and based on this we can calculate the magnetic moment. Option A is correct. We have option A is correct. If you like this video, please share and subscribe to the channel.